deposit resistance, right? So we want this to be as flat as possible. So now let's look a little bit closer, right? I think earlier I kind of mentioned that, if the pole of this track and hold circuit is not far enough, you may not be able to catch up, right? So remember this is track and hold, right? The green curve. I showed that you can track and follow. So look at this purple curve. I intentionally make the pole small. So basically you take a long time to follow. So you see, when you're in the tracking period, you follow to this point, and then you hold. Oh, by the way, I forgot to mention, how do I hold? Hold. This is hold, right? Hold is when your gate of that amount is 0. So you turn off. Do I hold? So it's hold, right? So whatever that voltage you just kept on the capacitor. Okay, so yeah, so look at the purple curve, right? So if you are not having enough settling dynamics, right? The pole frequency is not high enough. You're gonna stop at some point and you're gonna hold there. And next time you are in tracking mode, of course you will still try to follow. You're still trying to catch up. But there's a certain speed that you can catch up, right? So where's my error? This is the error, right? This is the error. So whatever that delta is your error. Right? So this is your error. This is your error. Error 1, error 2. So every sample you have error. Okay, so that's why this is so-called the tracking bandwidth. So basically the RC pole is the tracking bandwidth. Okay, so here, as you can see, I do in series with another resistors, and the reason is because I kind of mentioned, right? So usually before your ADC or your sampling circuits, you have some kind of driver, okay, or buffer, whatever you want to call it. Okay, so that must have a certain output resistance, right? So you have RS. So don't forget about that. Sometimes people forget about this, right? They thought that, oh, the whole track and hold circuits, I just need to control. Calculate the unresistance of that sampling switch. Is not, right? You do have this RS coming from the from the driver. So this is from the driver. Okay, so your pole frequency is actually not 1 over R on and C. It's actually RS plus R on times C. Okay. So let me ask you, if I want to make sure that I have a wide tracking bandwidth, what should I do to the RS? Should I make it large or small? Small. How do I make a driver RS small? So basically I'm asking, how do I make output resistance of the amplifier small? Right? Yeah, so you open, then how do I figure the RS? Alright, so I need, if I want to low output resistance, you need to add output stage. Usually it's output stage, right? So you make the resistance low, right? So those are the different trade-offs to consider, right? So you do need to add those additional output stage to have a smaller RS, right? Usually you will take more power, right? That makes sense? You want to reduce that resistance. Yeah. Or you can put it in the feedback loop, right? Okay, so nevertheless, there's something to consider, and then you do want this at the very minimum, the 3 dB bandwidth. So this is 3 dB bandwidth of the track and hold circuit should be absolutely larger than your sampling rate at the very minimum. Okay, at the very minimum. Otherwise, your track and hold circuit will not follow. Okay, so now let's take a closer look. Okay, so this is what we call it as a track and hold circuit settling behavior. So what I'm gonna do is that I'm gonna give a step function. Okay, to the track and hold circuits. So usually this will characterize how fast your track and hold circuits can really cycle. So if the input is a step function, the output because there's a R and C, right? O, step function. So you know this point will look like a exponential function, right? Exponential function. So it will be like this. Right, so you want instantaneously goes up, it will take time, and then gradually will catch up. Actually, do they catch up? It never catch up. So unfortunately, yeah, as much as we hope, that's a sample and hold, right? So sample and hold, supposedly you should sample exact value. In real life, there's no such thing. There's always a tiny bit of errors right here. So first of all, do you agree that this error will go down as you give more and more time for the tracking? It does, right? It does. Yeah. For example, if you have 10 years to wait until the track and hold to follow, yes, you can. You can probably get really close. Okay. So in real life, you know there's gonna be errors, right? It won't be 0. It'll be some number. It can be 1%, 2%. I don't know. So the question is that if we cannot completely get rid of that, then we should at least understand what's our tolerance. Do you agree? You know, in real life you're gonna have error. Okay, so you know you cannot avoid, you cannot eliminate. Then you just try to make it as small so that you don't care. All right. So at what point that I don't care? Assuming this track and hold is for the ADC. Okay. To what point that I say, oh yeah, you are so small, forget it.
Below your delta. The error is
Below
LSB.
1 delta or 1 LSB. Very good. Very good, very good. In fact, throughout the semester, whenever I ask you this kind of question, you answer, yeah, less than 1 LSB. 99% you're right. Okay. Why? Why is that? You say that less than 1 delta you don't care?
Because you won't quantize it to a different one.
You remember the SNR? You have a signal power, you have a noise power, right? The SQNR is that you look at the conventional noise power. Imagine if the error that you're making is relatively smaller than that 1 delta. That mostly likely means that if you compute the power here, it will be much less than your conventional noise power. Does that make sense? If that's much less than the conventional noise power, that means that your actual SNR will be fairly close to your SQNR. Do you agree? Which means that your ENUP will be very close to N. Does that make sense? What's your ENUP? Your ENUP is computing from your SNDR. Right? So you see they are all tied together, right? So that indeed is the rule of thumb. All right. So mathematically for a low pass filter, right, R and C, how do I mathematically express this function, right? So I know you guys some of you already said that's exponential function. So that's exactly right. So this is V in. So V out will be V in times 1 minus exponential function. Okay, minus to the power minus t times omega 3 dV. Omega 3 dV is 1 over RC. Okay, so from this equation, obviously you can see if you have a lot of time, t, do you agree that this exponential function is gonna be very small? Very, very small. That means that BI could be. That's what we want, right? So this error is this. Okay. All right. This is a frequency spectrum of that track and hold circuit. I think we talked about this, right? So you do have a corner frequency right here, which is a pole frequency, right? So that's 1 over RC. And also, not just the frequency that matters, for the settling. Be careful about the group delay, right? Because we know that when you are getting close to the corner frequency, right? So you're gonna have a phase shift. Remember in 5 cases A, right? And the pole frequency you're gonna shift by 45 degrees, right? And the slope here is the difference, so be careful, right? So if your input frequency is closer to the corner frequency, you're gonna see some distortion, phase distortion, around that thing. So that's also another good reason why you wanna keep this corner frequency to be as high as possible, right? You wanna keep it as high, so you don't get close to your signal frequency. Otherwise, you're gonna have a distortion, right? Group delay will vary. All right, so, and then this one we just talked about, right? So you want that error to be within 1 error speed, right? One filter. And then remember earlier we talked about this R-on can be like this, right? So it's not flat, right? So some depends on what's the V in value. Sometimes the R-on can be higher. That means what? That means that this corner frequency will go up or go down. If R-on fluctuate higher, this will go down. Is that good or not good? It's not very good, right? Because your pole frequency, you want to keep as high as possible, right? Whenever you go low, you cause distortion, you cause a settling issue, you get all those nasty stuff, right? So, okay. So essentially, what that means is that if you don't keep it constant, sometimes still depends on the V value, right? Sometimes it will be higher, sometimes it will be lower, right? And you really worry about the lower bound. Okay, so you will vary. Okay, so let's look at a case where your tracking bandwidth is not sufficiently high. Okay, so this is the sine wave input. If you don't design the track and hold, so let's say it's a MOS. You don't push this RC high enough, right? You may get the sine wave like this. You see what happens to this sine wave? When the input voltage is low, this one seems to track it pretty well. But when it's high, do you see the delay? You see there's a delay. Why? But when you are low, you see they follow very, very well.
That pole frequency reduced because R-on is
right? Because here, your R is so high, your pole frequency is low, you have a group delay. Remember I talked about the group delay? You actually delay a bit more. Okay, so what kind of wave is this? Originally, it was a perfect sine wave. But then if I tell you that, oh, by the way, the top one gonna delay a little bit more. If I do FFT on this, because in the end of the day, you're gonna do FFT, right? Assuming you do proper windowing and all that. What does the spectrum look like? Is it noise floor goes up, or distortion, so it means that you have harmonics? Which one is it? Or both?
more distortion.
Distortion. Whenever you see this shape, looks funky and all that, that's distortion. What is noise? Noise means that you have things going up and down. That's noise, right? So this, even visually, you can see distortion. So distortion will go up. So what kind of ADC spec will be worse? SNDR, SDR, SFDR, THD, and probably SFDR will go up, right? SNDR, how about SNDR? Okay, it will be worse, right? How about SNR? Same. Okay, so you guys are expert now. So remember I told you that when you design for high speed, it's more difficult, right? Okay, so in light of track and hold, do you agree? If I do high speed, that means my tracking time will be longer or shorter. Has to be shorter. And then how do you maintain the same SNDR? Huh? How do you maintain the same SNDR, right? So it becomes more difficult, right? So that is why I said, right, when you design for high speed, you need to bow to them another 60 degrees, right? Yeah, and likewise, I also said that if somebody design one more bit, you should also bow to them 60 degrees more. Why is that? In light of this, if somebody design one more bit, why should we respect that person even more? Because your LSP is lower. That means your error tolerance is also lower. You just have to design more accurate circuits, right? So this is what I said. This is actually no joke. Design one more bit. Your speed is faster. You just need to really pay your respect to that person. All right. Okay, so because of that error tolerance, you can calculate. Okay. So this is the accuracy. So this is basically error tolerance. Okay, and this is the number of time constant. So this basically the pole frequency, right? So 1 over RC is your pole frequency. So usually they track with each other. Okay, if your ADC or your sampling circuits, you just need to be 10% accurate. Okay, you just need to put about 2.3 times of that time constant, the tracking time. If you want to design a 10-bit ADC, by the way, where this number comes from? This number, 1 divided by 2 to the power of 10, right? 10-bit. This is 1 LSP, right? 10-bit, so this is a good number to remember. 10-bit, 1 over 2 to the power of 10, so that's 1 over 1,000, about 0.1%, right? So 0.1% is about, you're talking about 10-bit ADC. In that case, you need to design your track and hold circuits to be at least 6.9 times the RC time constant. What is that RC time constant? That's RS. Remember RS plus R times C. That's that time constant. Okay, so no matter what you do, the higher the resolution of the ADC, your sampling speed go up or go down. Has to go down. You see that? So that's just trade-off. Right? You cannot just say that, oh, by the way, I want to design high resolution ADC. Oh, and I can easily get the speed also very, very fast. No, they don't go hand in hand. There will be a trade-off, right? You want to do high speed, then you trade off your accuracy. And likewise, if you want to be super accurate, then you need to give me time. You need to give me time so that the circuits can be more accurate. So this is the first evidence of showing you how difficult it is to get both at the same time, right? Speed and accuracy. Okay, of course you can say that, no, what do you mean? I can just reduce the RC value, right? Even though this constant number goes higher and higher, I can reduce the R and C value. Okay, so what does that mean by reduce the R value? How do I reduce the R, for example? Let's just start with that simple thing. So this is switch. How do I reduce R?
Increase width.
Increase
Transistor width.
W over L. You need to burn area and the power, right? What is the power? If you have a large device, you need to drive the gates, you need to burn more power. You see that? Basically, if the conclusion is that there's no free lunch, you need to burn more area, burn more power, usually you're right. Right? So, and then same as the RS, right? So this is one question I asked you, right? So if you amplify, you want to have a low output impedance, you also need to be generally burn more area and power. Okay, you probably most likely need to size up some of the things. Okay. So that's the first important lesson, right? So learn from the sampling circuit perspective or tracking whole circuit perspective. There's always an interesting trade-off, when we design a circuit. There will be other techniques to deal with this signal dependency. Okay, so there are actually quite a few, so I will discuss later. But at this point, it's okay that we stick with this simple R and basically one switch and one capacitors. It's a starting point. Okay. Any question? Okay. Next, so we just finished on the tracking bandwidth impact, and now we can what we should design for it. Next is so-called the aperture time uncertainty. Okay. So far, whenever I draw the clock, so let's use just one switch and one capacitor. Okay, so that's the easiest. The clock usually I draw like a square wave, right? Square wave. In real life, is there a square wave for the clock? It cannot, right? There's a certain rise and fall time, right? You heard about rise and fall time, right? So there's a certain slope, right? So in reality, there's a certain rise and fall time. And by the way, so when this is high, this is in tracking mode, right? And when this is low, this is in the hold mode, right? So where is the sampling instant again? The delta function, remember the delta function? It's between track and hold, right? So it should be in the folding edge. Do you agree? In the case where I use a MOS as a switch. Okay, so it's always the folding edge of that sampling clock that will determine your sampling instant. Okay, so now let's zoom into the instant. Okay, so we know that's the most important instance because that's where we're gonna, capture the analog voltage. So as I said, if I zoom in, especially in the folding edge, right? So there is a certain fall time. Where's my actual sampling instant? So your clock will go from VDD to ground, right? So ideally speaking, you want the sampling instant to be half, right? How about that, right? I think in digital circuit, they also assume, okay, just half VDD. That's your trip point, right here. But if you examine this real carefully, this is VCK, this is V in. So if you look at this MOS switch, tell me when is the point that will go from triode to off? When VGS equals to VTH, a square law device. Right now I'm assuming the square law device. Do you agree? This is gonna be my sampling instant when VGS equal to VTH. Okay, so where is that instance? So what is my VGS? V clock minus V in equal to VTH. So far so good? Okay, so I'm gonna move this to the right hand side. So basically the sampling instance is gonna be when V clock equal to V in plus VTH. Do you agree? This is the point where you actually will determine the sampling instant. Is this a constant value? It's not. Why? Because if I plot V in plus VTH, which is a plot here, V in, for example, can be a sine wave, right? So if it's sine wave like this, so where is my actual sampling instant? When VCK equal to this value, right here, is my actual sampling point. Remember the delta function? This is the location of the delta function. Okay, what if my sine wave change a little bit, it become like this? Where is my sampling instant? Okay, sorry, I should say that V in plus VTH, right? Don't forget the VTH, right? Threshold voltage. Okay, so V in plus VTH we go from there. So before it's here, now you shift to here. So what is my actual sampling instant, right? So you may be sampling the point where you think that, okay, yeah, it's just at the falling edge, and then even if there's a finite fall time, you're gonna assume that's a VDD over 2, right? That's usually how we assume. By the way, that's still a very reasonable assumption, right? So to the first order, that's what we assume. But if we zoom in, we realize that no, that's actually not the case. Sometimes it will be earlier, sometimes it will be later, right? So you actually have some error of degree. Your sampling point, you think that you just sample at this point, but it will shift a little bit, right? So that is what we call as the aperture time uncertainty. Okay, so of course, we need to analyze what's the impact. So what I'm gonna do is that I'm gonna assume the input is sine wave, which is certain amplitude. Okay, A times sine omega t. For now, I'm gonna assume the threshold voltage is gonna be very small, because I know I need to compare to V in plus VTH, right? But it's very small. So what I'm gonna do is that I'm just look at the sine omega t, which is V in, divided by the slope of this clock. You see the clock here, right? There's the slope right there, right? So basically, whatever that input value divided by the slope will be the time you actually change. Okay, so basically like phase modulation. If you take a communication class, it's like a phase modulation. All right, so we're gonna divide it by the slope of the clock. So rise fall time of the clock divided by the V clock. That is the slope of the clock. Okay, and the TRF is the rise fall time of the clock. Okay, so basically the sampling instant will be actually get modulated by this delta T shift. Okay. So your output is still a sine wave, right? Still a sine wave amplitude A omega t, except that I get phase modulated T plus delta T. Okay, so A sine omega t plus delta t. Delta t, we just do this first order approximation, sine omega t divided by V clock over TRF. Rise fall time. Okay, so apply the equation that you learned from trigonometry. So this A sine of the two number, right? X plus y is sine times cosine plus cosine times sine. If you remember, if you forgot, it's okay. You can easily find from internet all those trigonometry equation. So you can just expand it, sine omega t times cosine. Okay, and I'm gonna introduce a new variable called tu, sine omega t plus a cosine omega t times sine omega tu times sine omega t. And tu here is a over bck times trf. Okay, so tu is this, and then you want this TRF to be very small, right? Relatively small, right? The clock rise fall time is relatively small. So tu in the end of the day will be a small number. So this argument here would be small. Okay, I want this to be small. So cosine theta, when theta is small, what is the value? Cosine theta when theta is very close to 0. 1. So it's a sine omega t plus A times cosine omega t times sine theta when theta is small. What is that?
Yes, sir.
Approximately sine theta, theta, right? When theta is small. Okay, so I can take this out, right? The sine theta when theta is small. So this is omega tu times sine omega t. So what we got in the end is A sine omega t plus A times omega times tu times, what is the sine omega t times cosine omega t times sine omega t? 2, yeah, so this is 2. Yeah, you have a very good memory. So you have sine 2 omega t. And then divide by 2. Right? The sine 2 theta is 2 times cosine times sine. Right? Did that bring back your memory to high school? Alright, so this is my fundamental frequency, which is my input sine wave, right? So this is basically my input. Because A times sine omega t is my original input, right? Remember? The phase modulated output, right? At the output of track and hold, you still have the input, thanks God, right? I mean, if you lose the input, then what's the point? We are not sampling, right? So you still have the input, but look at the second term. What is that second term? On the spectrum, right? So assuming this track and hold is gonna be used by the ADC, and the output you do FFT, what do I see? What is this? Noise floor or distortion? It's harmonic distortion. Not only I know this harmonic distortion, I know exactly what harmonic. Which harmonic is this? Second harmonic. Right, this is what we call second harmonic, because you have a 2 omega t. Okay, so we're done. So this analysis just kind of teaches us that what to expect. Okay, so if you have this aperture uncertainty because the actual crossing point, right? So your sampling instant shift, what it comes down to, congratulations, you get the second harmonic. This is why I said that you look at ADC output, you're gonna see those spikes. So this is one of the many reasons. Okay, so I'm out of time, so I'm gonna stop right here. But at least this part analysis, I'm almost done. When we come back on Friday, I will give you some